Hello everyone, my name is Alexa Limón Bonilla. I'm studying a bachelor's degree in biotechnology at the Benemérita Universidad Autónoma de Puebla, and today I'm going to talk about in what ways can different spectroscopy methods help us to confirm and better understand the special properties of indium phosphide quantum dots. It is well known that in recent years, the synthesis of semiconductors nanocrystals has opened a possibility in the design of new materials or devices with unique optical, electrical, thermal, and biological properties. One of the main areas of scientific interest is to generate new applications such as photoluminescent devices, diode lamps, screens, photodetectors, photovoltaic devices, solar cells, and biological markers. So, how does this can turn to reality? First of all, we have to talk about our protocols. Our synthesis was a one-path method in which we put all the precursors in just one phase. In this case, chloroform and octadecane were the precursors. After the synthesis, we obtain our colloidal quantum dots that we can see there on their UV light, highlighting its photoluminescence. For the last step, we deposit the quantum dots on Corning glass to determine their characteristics for each technique. The first technique to discuss is photoacoustic spectroscopy or PAS. This was used to investigate the optical properties of quantum dots in two different solvents. For indium phosphide quantum dots in chloroform that are sample H1 show a sharp absorption peak at around 300 nanometers, followed by a gradual decline, while the quantum dots in octadecane exhibit a less defined band showing the solvent impact on the optical properties. For sample H3, we can see a minimal change between the solvent, suggesting it is more stable or less sensitive to the solvent environment. Moving on to the thermal lens spectroscopy, we know that this technique is used to investigate the thermal diffusivity, measuring the changes in the refractive index caused by localized heating. And in this case, we're gonna see how does the quantum confinement influences heat dissipation. Sample H1 exhibit the highest thermal diffusivity at 0.005, consistent in a strong quantum confinement and a smaller particle size. For sample H3, we have that show a lower diffusivity of 0.003, suggesting a larger particle size. The results are aligned with the inverse relationship that says that smaller quantum dots show higher thermal diffusivity. And finally, we have photoluminescent spectra. This is used to study the optical properties of materials. When a material absorbs photons and then re-emits them, this process is known as photoluminescence. Photoluminescence spectroscopy show that samples H1 at 300 Kelvin exhibit a broad high energy photoluminescence peak near 3 volts, indicating a strong quantum confinement effects. In contrast, H3 showed the most intense photoluminescence signal among all the samples, with a sharp emission peak around 2 volts. The high intensity of this sample, H3, suggests highly efficient radiative recombination, which means that excited carriers recombine directly by emitting photons efficiently with minimal energy loss. When non-radiative processes are present, excited carriers lose energy through several intermediate steps before they can emit a photon, making photoluminescence slower and less efficient. However, in samples where the indium phosphide bonds are properly complete, radiative recombination becomes dominant, allowing for a brighter and faster photoluminescence response. In H1, the broader and less intense photoluminescence peaks suggest a higher influences of non-radiative recombination, while the sample number 3, the half sharp and intense emission, indicates better optical performance. Finally, thanks to these results, we can confirm and understand the special properties of indium phosphide quantum dots by showing how they absorb and emit light and how their surface and solvents affects this process. This knowledge is important because indium phosphide quantum dots can be used in many applications like biomarkers, solar cells, devices, screens, cameras, and such much more. Thank you.